Our topic is digital comparator and 2 bits magnitude comparator. Comparator is a combinational circuit which compares two binary numbers whether they are equal or not. An exclusive NOR gate is the basic comparator circuit in which we have two inputs and one output, and if we give 2 bits at the input, then it will compare these 2 bits, and if these 2 bits are equal, then at the output we will get one state, and if these bits are not equal, then at the output we will get zero state. A magnitude comparator is that in which we have three outputs. If we have two numbers A and B, A is equal to A1 A0 and B is equal to B1 B0, which shows that each number is of 2 bits. Then the comparator will compare these two numbers which are given at the output, at the input, and at the output it will give us three values: A is less than B, A is equal to B, and A is greater than B. So this type of comparator is called the magnitude comparator. Now its block diagram is in the block diagram. We have four inputs of two numbers A and B, and these bits are A1, A0, B1, B0, and at the output we have three outputs G, E, L. G is A is greater than B, E is equal to B, and L is A is less than B. Then we will draw the truth table. In the truth table, we have inputs and outputs. On the input sides, we have A1, A0, B1, B0, and at the output side, we have three columns: A is greater than B, A is equal to B, and A is less than B. In the first row, we have 0, 0, 0, 0, and clearly these two numbers are equal, and therefore we will write one state in the column A is equal to B and 0, 0 state in the other two columns. In the second row, we have input side is 0, 0, 0, 1. Clearly the number B is greater than A, and therefore in the particular column of A is less than B, we will write one state and other two columns 0, 0 state. So in this way all the truth table is drawn. Then we will write relations for G, E, L, and if we want to write the relation for G, we will see the column of G, and corresponding to each one in this column, we will write the min term. So all the min terms corresponding to 1 in this column are noted, and then by adding all the min term we will get the relation of G. Similarly, we will write relation of E by looking column of E, and the main term corresponding to 1 in this column is noted, and by adding all the main terms we will get the relation E. Similarly, we can write the relation of L. Now we can draw K-maps to simplify these relations. Clearly we have 4 input variables, and therefore the square of the k map will be 2 raised power 4, which is equal to 16. So we will draw k maps for 16 square for each relation. In the figure, we have the k map for G, and we will write 1 in the corresponding square of the main term given in the relation, and then we will see the adjacent squares. We can combine the adjacent squares, and then we can write the simplified relation for G. Similarly, for the relation E and L, we can draw K map, and then we will write 1 in the corresponding column of the main term available in the relation, and then we will make the groups of the adjacent squares, and then we can write the simplified relation. At last, we will draw its logic diagram. Now we can see in the K map of E, we have 1 in the corresponding squares, and we can see that no one square can be combined with any other square because these are the not adjacent squares, so the relation for E will remain the same. And similarly, we will draw another K map for L, and then we will write 1 in the corresponding squares of the min term available in the relation of L. Then we will make groups of the adjacent squares, and then we can write the simplified relation for L, and then we can draw the logic diagram. In this logic diagram, we have 4 values A1, A0, and their complements B1, B0, and by connecting inverters, we can get these values, complemented values of A1, A0, B1, B0, and then we can draw the 3 AND gates for A is equal to A is greater than B, and then an OR gate, and at the output of the OR gate we will get A greater than B. Similarly, 2 exclusive OR gate are drawn for A is equal to B relation, and then 1 AND gate, and at the output we will get the required relation. Then we can draw the 3 AND gates and 1 OR gate for the relation A is less than B.